So today we are going to talk about connected components. And we are going to discuss a depth first search based method to find the connected component. Okay. So let's first look at a sequential algorithm, right? How would a sequential algorithm work? Right. So one simple way is that you perform a depth first search, a DFS traversal on the whole graph. Okay, so what's the outcome of a DFS traversal on a graph? Well, you'll get a forest, right? Not necessarily a tree, but you could get a forest if it's not connected. Yeah. Okay, and we know that each tree in the final forest is a connected component, right? So we are talking about undirected graphs here. All right. So what's the sequential runtime? Runtime of the sequential algorithm? Well, you have to at least visit all the edges, right? So you have to visit all the edges. That's pretty much the amount of work that you have to do, right? And this would be theta n square for a dense graph. Yeah. So now the question is, how do we come up with a parallel formulation? So the parallel formulation is basically going to be a parallel formulation for DFS, right? So essentially we have to do a parallel version of depth first search, right? And then figuring out the connected components is straightforward. Okay. So connected components pretty much boils down to depth first search, right? And we're trying to do that in parallel. So how do I do a DFS in parallel? There are three things that I have to take care of. Okay. The first is I want to partition the adjacency matrix into P parts. I want all the processes to be doing some work. Yeah. So what we're going to do now is that we will have each processor compute DFS forest on the graph visible to it, right? Whatever graph it has, it's going to compute a DFS over that, a DFS forest, right? We'll go through an example to understand this better, but the problem is that the same connected component may not be completely visible to one processor. So different processors may be seeing different parts of the same connected component, and they may not have the full view of the connected component, right? Therefore, there is an additional step involved over here, and that is that we have to merge the forests to get the complete final forest, right? And therefore, this will give us the connected components. All right. So the strategy is clear. That's what we're going to do, right? And we are not going to write the pseudocode for this one. Let's just understand what happens, right? How this is implemented. So the very first thing is, let's look at issue number one, right? How do we partition the adjacency matrix into P parts? Yeah. So let's take an example and maybe, try to understand it via that. So we are going to do a row-wise partitioning of the adjacency matrix. Okay, so let's take an example. So let's say that I have the following graph, right? I have a vertex 1, 2, 3, 4. All right, so I have this graph. It has two connected components. And let's see what the adjacency matrix for this would look like. 1, 2, 3, 4, 5, 6, 7. So there will be 7 rows, right? And there'll be 7 columns. Okay. And what will be the entries over here? So from 1, there is an edge to 2, 3, and 4, right? All the other entries are 0. From 2, there's an edge to 1 and 3. All other entries are 0. From 3, there's an edge to 1, 2, and 4. From 4, there's an edge to 3 and 5. From 5, there's an edge to 3 and 4.
There's an edge from 1 to 4 also.
There's an edge from 1 to 4, 4 to 1. Yeah, sorry. Okay. And 5 is done. 6 only has an edge to 7. And 7 only has an edge to 6.
There's another edge from 3 to 5.
3 to 5. I'm missing entries. Huh? Okay, 5 to 3 is covered. Okay. Okay, good. All right, so this is the adjacency matrix. And now, how do we partition it? So we'll do a row-wise partitioning of this adjacency matrix. So let's partition it, maybe give 3 vertices. Let's say there are only 2 processors, right? Just for simplicity, just to understand how this algorithm works. Of course, this algorithm extends to P processors, right? So let's say this is P1 and this is P2, right? So P1 has this view of the adjacency matrix and P2 has another view of the adjacency matrix, right? So P1 is aware of all the connections of the edges 1, 2, and 3, even though the other vertices do not reside on P1, right? Is that clear? So actually P1 does not own a subgraph per se, right? This is not a subgraph because it's kind of like it can see all the 7 vertices, but it can only see the edges for 3 of them, right? Let's first see what is the graph visible to P1, right? This is the graph visible to P1. So it can see all the edges from 1, 2, and 3, right? So it can see all the edges from 1, it can see all the edges from 2, it can see all the edges from 3. That's it, right? So 6, it knows these vertices exist, but it doesn't see any edges over there. Yeah, is that clear? Okay. And what is visible to processor 2? Processor 2 sees all the edges from 4, 5, 6, and 7. So it sees the same vertices. 1, 2, 6, and 7. Yeah. But it only sees the edges from 4, 5, 6, and 7. So 4, 5, 4. Okay, 4 has another edge to 1. It sees all the edges from 4, 5, 6, and 7. Yeah, is that clear? So look, to view a depth first search, right, you have to think more in terms of edges rather than vertices. So some of the edges will be visible to both the processes, right? If one of the vertex endpoints is owned by P1 and the other vertex endpoint is owned by P2, then that edge will be seen by both P1 and P2, right? All right, so these are the view that's visible on the two processes. So how many connected components are there? There's one connected component, second connected component, and third connected component, right? And here also there are three connected components, right? 1, 2, and 3. Okay, so now what it's going to do is P1 is going to build a DFS forest over this graph, the red graph, and P2 is going to build a DFS forest over the green graph. And then we have to merge these forests. So now the important point is, how do we merge them? Let's go back to the three issues that we wanted to look at, right? So first we partition the adjacency matrix into P parts. So we've already decided how to do that. Then each processor computes the DFS forest on the graph visible to it, right? So we can compute this DFS on P1 and P2. So how much time is it going to take to compute this DFS? So this is step 2, right? So DFS on each processor. How long is that going to take? Well, it's theta of the number of edges, right? So here, the number of edges that are visible is n square by p, right? So this is an n cross n matrix, right? That's n square entries, but they're divided over p processes. So it's going to be theta n square by p. Is that clear? Theta n square is the size of the adjacency matrix. And since we divide it almost evenly amongst the processors, the number of entries on each processor is theta n square by p. Okay. So this is essentially nothing but the number of edges or entries of the adjacency matrix visible on each processor. All right. So let's build a DFS. On P1, the DFS may look something like this. You have this vertex 1, vertex 2, 3, 4, and 5, right? That's a DFS tree on P1. Sorry, I also have to keep track of 6 and 7. So this is the DFS forest. And what about P2? Well, if I start from 1, I will build 1, 4, 3, 3 will connect to 5. Yeah. And 2 will be a separate vertex, and 6, 7, yeah. This will be the forest on P2. You could have done it in different ways, but that's fine. Okay. Okay, so that's step number 2. We've built the depth first search forests on each processor. And now finally, we have to merge these forests, right, to get the complete final forest. So how do we merge these forests? That's the important part now. So essentially after the merge, right, this 1, 2, 3, 4, 5, all of this is going to become one connected component, and 6 and 7 is going to become another connected component, right? So what do we mean by merging the forests? So we are not going to get into the algorithm details, but it's basically called the union find data structure, right? And typically, what do you use for this? You use an algorithm based on ranking and path compression. Okay, so again, this is something you probably studied in your algorithms course. But anyways, we are not going to get into this, okay? You can read up on it. I can give you some rough idea about what it is, but we are not going to get into the analysis, right? It's not something that's part of this course, and it's more appropriate for an algorithms course. It'll take up too much time. Okay, so how does the union find data structure work? So you deal with sets, right? So we are going to work with sets. So there are three operations that you can perform. Either you can make a set, right? So that's like creating a set. It's a basic operation. The two important operations are find and union. Okay, what does find do? So if you say find a vertex u, right, it's going to return you some identifier of the set it belongs to. And if you do a merge operation, right, you give two vertices and these come from different sets. Right? It's going to merge the two sets. It's going to take the union of the two sets. Union or merge the two sets that u and v belong to. You could have specified the set identifiers instead of the vertices u and v. That's fine, right? You can have different interfaces for this. Either you specify two vertices in these or you specify the identifier of the sets. Right? So this is basically the kind of operations we want to support. So we are interested in connected components, right? Not in the DFS tree. So I'm going to create sets over here. Here I'm going to create the sets. One set is going to be 1, 2, 3, 4, 5, right? Another set is going to be 6 and another set is going to be 7. So there are three sets on P1, right? One corresponding to each tree in the forest. Yeah, is that clear? Okay. Similarly, I'm going to have sets over here. The sets are 1, 3, 4, 5. Then there's going to be a set 2 and there's going to be a set 6, 7. Yeah, is that clear? Now we want to merge these. So how can I merge these? So here is what I do. So let's say I'm given two forests, right? Let me try to define it more generically. So we are given two forests. A and B, not trees, forests, right? We want to merge these forests. I examine one of these forests and I look at all the edges present in that. So what I'm going to do is I'm going to merge A into B. That means I'm going to update B. Sure, you can do it other ways also. You can create a new forest and so on, but I'm just showing you what I'm going to do in this algo, right? Now I look at each edge. For each edge, UV in A. I'm going to first find U in B. Okay, I'm going to do the find operation for the vertex U in the forest B. Okay, I have to tell you which forest I'm doing it in because look, the vertex U is part of two forests, A and B, right? One is held by processor 1, one is held by processor 2. So when I do a find operation, it's going to give different results depending on which forest I do the lookup in. So we have to be clear that where are we doing the find operation, right? So we are doing the find operation in B. All right. Similarly, I also look up, I do a find operation on the vertex V in B. Okay. And now I check if X is not equal to Y, then I merge UV or merge XY, depending on whatever the interface is, right? I merge the two sets. Where do I merge them? I merge them in B. Okay, that's the important part. So as I said, right, I'm going to modify B. I'm going to update B by looking at A. After that, I'll just discard A, right? I don't need that forest anymore. Is it clear? So let's see this executing, right, on the example that we had. Yeah, before we execute it, how many times for each edge UV in A, how many iterations does this involve? Well, at most n-1, right? There aren't more than n-1 edges in any forest. Okay. All right. Let's run this algorithm on the example that we just had. So this is what A has. 1, 2, 3, 4, 5, and then 6, and then 7, right? 3 sets. And what does B have? It has 1, 3, 4, 5. 2 is separate and 6, 7 is together. Okay, these are the 3 sets on B. So I'm going to look up every edge in A, in the forest A. So what are the edges in A? So we're talking about the forest. 1, 2, 2, 3, 3, 4, 3, 5. 1, 2, 2, 3, 3, 4, 3, 5. Is that clear? I think these are the only 4 edges, right? Okay. All right. So now let me start running this algo, right? So first I'm going to look at this edge 1, 2. Let us associate some roots, right? So some identifiers, right? So one way of associating an identifier is the root of the tree in the forest becomes your identifier, right? So I need to associate some identifiers. So I'll call 1 as the root of this, 2 as the root of this, and 6 as the root of this, right? Just for the sake of having some identifiers. Okay. So this has root 1. This obviously only has one root. This has root 6. Okay. So the first thing I do is I do a find on 1, 2. What does the find return me? It returns me 1 for one and 2 for the other, right? Where am I doing the find? I'm doing the find in B, in the forest B. So it returns me the root 1 here and the root 2 here. Okay. So I see that these belong to different trees, different sets in the forest B. Yeah. And so therefore I'm going to do a merge operation. So I should probably write it over here. So I'm going to do a merge in B, right? So I'm going to do a merge of 1 and 2. So here I'm using the notation of the roots. Let me circle it for clarity. Let me put all root IDs in circles. Okay. So I'm going to merge 1 and 2. So what do I get? Well, now I get 1, 2, 3, 4, 5, and I get 6, 7. Okay. Now I look at 2 and 3. Well, if I do a find on 2 and 3, what am I going to get? I'm going to get 1 for both of them. One more thing has to happen. When I merge, I have to have a single identifier for the set, right? So one of these identifiers is going to change to the other. So let me, for simplicity, again, assume that, we associate identifier 1 with this new set, and this continues to remain 6. So identifier 2 is not valid anymore. Yeah. Okay. When I look at the next edge of A, I see the edge 2, 3. I do a find operation on B. I find that both of them belong to set 1, and nothing to be done. All right. Again, I look at 3 and 4. I perform a find, and I see that both of them belong to 1, 1. Nothing to be done. I try to merge 3 and 5. I see that both of them already belong to 1, 1. Again, nothing to be done. So this is the merged forest. What I have at the end of this is the merged forest. Yeah, is that clear? And that corresponds to the connected components.
So this was done when we had two processors. When what if there are more than two processors? In that case,
Correct. Right. Okay, so in that case, we have to perform log p iterations to merge pairwise, right? So first P1, P2 will get together, right? Merge their forests, right? Then P3, P4 will get together, merge their forests. P5, P6 will get together, right? So this will happen in iteration 1, right? So let's call this forest P1, this one P3, P5, P7. The forest is held on these processes, let's say. right? Then I merge P1, P3, I merge P5, P7, P1, P5, and then I merge these two forests. Right? I get the final forest. Okay, so this is going to take log P steps. Yeah? Iterations.
Yes.
Log P. Yeah. And it's clear, right, that the final forest or set, if we are maintaining sets and doing merge and so on, right, we don't have information on the edges so far. You can maintain it in parallel, but it's not required, right? So you could just be working with sets. So final set give you the connected components. Okay.